lecture, we are going to talk about AlexNet. Uh, before and in the previous lectures, we have talked about neural networks, perceptron. Then we talk about convolutional neural networks for classification of digits dataset. In this lecture, we are going to introduce the AlexNet, and using the AlexNet, what we will do, we will perform the classification of images for C10 dataset, classification using AlexNet for C10 datasets. So in this notebook, we are going to implement a modified version of AlexNet that uses convolutional network layers and was designed for ImageNet challenge. AlexNet is famous for winning combination of ImageNet challenge 2012, beating the second place competitors by 10% accuracy and kickstart interest in deep learning for computer vision. The image below shows the architecture of AlexNet, where it is the input layer. Then there is the convolutional layers. The first convolutional layer has a size of feature map 55 by 55, and there are 48 such filters. Then the next convolutional layer, it has a feature map of 27 by 27, and there are 128 such filters, number of filters, number of feature maps. And then the third layer has a size of feature map of a size 13 by 13, and there are 192 such filters. So this is the architecture of the AlexNet, which has convolutional layers and max pooling layers. So confusingly, there are two paths for processing through the network. This is due to original AlexNet model, which is being implemented by two GPUs, a GPU 1 and GPU 2. But almost all implementations of AlexNet are on single GPU now, and we will implement the same single GPU implementation throughout this lecture. We are now moving from the MNIST dataset, and from now onward, we will be using C10 dataset. C10 dataset, it consists of 60,000 images of size 32 by 32, and there are 10 classes in these images, and with each class has about 6,000 images. The number of the classes which are in this dataset are aeroplanes, um, automobile, birds, cats, deer, dog, frog, etc. So here are some of the images. We will also show how to utilize the weights of neural networks and find the suitable learning rate. So we will discuss, like the previous notebooks, we will implement our model and measure its performance on the data set, and then have a look into seeing the model, what it has learned. Most of the notebooks are similar. Okay, so in the data processing, we will follow the data processing, and we will import the different modules and libraries from the torch, from the PyTorch. So we are going to import different libraries: torch, neural network, function optimizer, learning rate scheduler, etc. So I run this cell, and then I am going to import different libraries. So we set the random seed so that experiment can be reproduced. So we are going to set the random seeds. We calculate the mean and standard deviation of our data. Since our data set has colored images, and which are composed of three channels, red, green, and blue. Previously, we were using MNIST dataset, which has only two single channel, black and white images. So we normalize these color images and compute the means and standard deviation for each of the channels independently. To do this, we pass a tuple containing the axes. We want to make the means and standard deviation over the mean and standard deviation function. So we are going to import the we are going to fetch the data C10 dataset. We are going to download it from the website, and then we are going to print the mean and standard deviation of this dataset, mean for each channel and standard deviation for the each channel. Next up is performing or defining the transformations for data augmentation. The images in the C10 dataset are significantly more complex than MNIST dataset. There are larger have 3 times the amount of pixels and more cluttered. This makes them harder to learn and consequently means we should use less augmentation. So here we are going to use the horizontal flipping, which we did not use previously with a probability of 50%. Because if we flip the digits horizontally, then they change the meaning of the digit. For example, if we flip 5 horizontally, then it becomes some other shape. So flipping digits is not useful, but flipping the images that is meaningful. For example, a face of a face of a car maybe on the right side, front side of a car maybe on the right side, but when we flip, then it's front side, bonnet side, it goes on the left side. So we define different transformations, horizontal rotation, horizontal flip, and random crop tensor, and we define very few transformations for the test set. For the training set, we define more transformations as we did in the previous case. Then uh, then as a standard, we load the data set with our transforms. We perform the transformation on our data set, and then we what we do is we segregate the validation data set, and we say that the 90% of the data is used for training and 10% for the validation. Here we copy the validation data set, and then we print out the number of examples then each of the data. For example, the number of examples in the training set, validation set, and test set, they are 45,000, 5,000, and 10,000 respectively. Now we create a function to plot images in our dataset so that we can actually look or visualize those images. So by default, PyTorch handles the images in the form of channel, height, and width. But matplotlib, it takes the height, width, and channel. So we keep in mind while plotting these images. So here we are going to define a function for plotting the images and their labels, and then we actually plot the images. We get both images and the labels from the training data set and convert the labels which are originally stored as integers. We then plot them and see the warnings and matplotlib. So here we are going to plot, I guess, 25 images. We are going to plot. So here it randomly took 25 images and it plot them: bird, dog, bird, deer, etc. So a solution to this is to renormalize the images. So each pixel is between 0 and 1. So again, it has renormalized these images. This is done by clipping the pixel values between the maximum and minimum within a range and then scaling it. So it is going to plot these images. Again, I guess rescaling: horse, automobile, frog, dog, ship, etc. So deer, dog, bird. We will be normalizing our images by default from now onward, and we will write a function that does it, which we have whenever we need to renormalize the image. So here we are going to define a function for renormalization, for normalization, and then we as before, we will check what images look like with Sobel filters when applied to it. We apply some filters on these images. For example, it applies the Sobel filter, and the filter are still two-dimensional, but they are expected to the depth of 3 dimension inside the plotter function. Below is a filter which detects the horizontal lines. So here is a filter which detects the horizontal lines. These are the horizontal lines are shown. These are horizontal lines are prominent. Horizontal lines are prominent here. And then we define a filter that plots the vertical lines. And you will see that the vertical lines are more prominent. So you can see that vertical lines, they are more prominent in these images. We will also do the same for subsampling and pooling. We will apply subsampling and pooling. And As before, the higher filter size in the pooling means more information is lost. That is, the image becomes lower dimension. So when pooling filter size is larger, then the image size becomes smaller. So here the pooling size is 2, and then we gradually increase the pooling size. You see, when the pooling size is increased, the image is more blurred or weird shaped. And then here it is when we are going to use the average pooling. Before it was the max pooling, and now we are going to use the average pooling. So average pooling of size 2, a filter size 2, average pooling of filter size 3. The final bit of the data processing is creating the iterator, and we will create the iterator. We use a much larger batch size here than in previous model. Generally using GPU, a larger batch size means our model trains faster. Our model has significantly more parameters and images. It is training on much larger than the previous notebook. So we generally take longer. We offset this as much as we can by using the batch size of 256 instead of 64. So initially we keep the batch size larger, and then we gradually drop down the batch size if there is some memory problem. So then we divide our data set into train valid iterator and test iterator. Then next comes the defining the model. The actual model itself is no more difficult to understand than the previous model, AlexNet. It is made up of convolutional layers, pooling layers, and ReLU activation functions. See the previous notebook for refresher. Okay, so there are only two concepts introduced here: NN sequential and NN drop out. Uh, we think of sequential as like our transforms introduced earlier. For data augmentation, we provide sequential with multiple layers, and when the sequential module is called, it will apply each layer in order to the input. There is no difference between using a sequential and having as much module defined in it, and then call forward. However, it makes the code significantly shorter. Using the sequential, the code becomes shorter. We have now sequential model features for all the convolutional and pooling layers, and then we flatten uh, the data and pass it to the classifier. Another sequential model which is made up of linear layers, and second new concept called dropout. Dropout is a type of regularization. As our model gets larger to perform more accurately on richer dataset, then they start having a significantly higher number of parameters. The problem with lot of parameters is that our model begins to overfit. This is they do not learn general image features while set learning to classify images, but instead they simply memorize the images within the training set. This is a bad as it will cause our model to achieve poor performance on the validation and test set. To solve this problem, we introduce or use the regularization. Dropout is just one method of regularization. Other common methods are L1 regularization, L2 regularization, and weight decay. Dropouts works by randomly setting a certain fraction, 0. 0.5 here, of neurons in a layer to 0. This effectively adds noises to training of the neural network and cause neurons to learn with less data as they are only getting half of the information from previous layer with dropout applied. It can also be thought of as causing your model to learn multiple smaller models with less parameters. Dropout is only applied when the model is training. It needs to be turned off when validating, testing, or using the model for inference. Then there is no need for the dropout. As mentioned in the previous notebook, during convolution and pooling, the activation function should be placed after the pooling. activation function is placed after the coding layer to reduce computational cost. In the linear layers, drop out should be applied after the activation function. Although when using redu activation functions, the same result is achieved if dropout is before or after. One last thing to mention is that very first convolution has input channel of 3 because we are handling or we are using colored images instead of single channel grayscale images of MNIST dataset. This does not change the way any of the convolutional filter works. It just means the first filter has a depth of 3 instead of 1. So first filter has a depth of 3 instead of 1. So here it is going to define the AlexNet as a class, uh, has the convolutional layers, max pooling, redu, convolution, max pooling, redu, convolution, redu, convolution, redu, etc. So here is and there is here's the forward pass. We will create an instance of our model when the desired amount of classes. So our output is equal to number of classes, which is 10. C for 10. There means there are 10 classes in this dataset. Then we will see how many trainable parameters our model has. AlexNet structure has 44K parameters, but here we have 23.2 million parameters, and AlexNet is relatively small model for computer vision. We define the count parameters and print the number of trainable parameters. Next up, we will initialize the parameters of our model. PyTorch's default initialization is usually fine. However, manually training different initialization schemes we can usually squeeze out a slight performance improvement. We initialize parameters in PyTorch, creating a function that takes up a PyTorch module, checking out the type of module it is, and then using and then init methods to actually initialize the parameters. For convolutional layers, we will initialize the weights of a normal distribution with the standard deviation given by kn divided by fn. So here it is the formula for choosing the learning rate uh, or initialize the parameter. So here we define a function that initializes the parameter. We apply initialization by using the model's apply method. This will call the given function on every module and submodule. So we apply model apply initialize parameters. Next up is learning rate finder. The code is taken from a stripped down and slightly modified version of this learning rate finder. So learning rate finder is more art than a science. So here you can read out the description for this learning rate finder. So here we define the class for learning rate finder, suitable learning rate. To prepare to use the range finder, we define an initial very low starting learning rate, and then we create an instance of optimizer we want to use with that learning rate. We then define the loss function we want to use. Define the loss function optimizer. Adam, we change it to CUDA cross entropy loss, then change it to criteria, and for this for optimization. Next, finally, we use the range finder. We first create an instance of the finder class, optimizer, and loss function and device. Then we use the range test with the training iterator, maximum learning rate, and the number of iterations that we want. That means that we are going to use, I guess, early stopping. Next, we plot the learning rate against the loss. As our learning rate was scaled exponentially, we want to plot it on logarithmic scale. We don't want to plot the last few values. They're usually where the loss is very high. and makes it difficult to examine the graph in detail. So here is the how we plot the learning rate, and then we can see the learning rate begins flat and then it begins to decrease rapidly before reaching a minimum and starting to increase. So here it is the we plot the learning rate, and now we can create a new optimizer with our found learning rate. Ironically, learning rate value we found is 0.00 is actually Adam's default learning rate. That is the best, I guess, 0.003. And we use this learning rate, and then we define the function for accuracy, and we define the function for training loop or for the training, and we define a function for evaluation or testing or validation of our model. We define a function for computing the time for each epoch, and then we go for actually training the model. Here for the in this notebook we will run it for one epoch, and the accuracy will be I guess low, but originally this notebook was running this model for 25 epochs when for that case the accuracy was about 76%. But this in this situation the accuracy would be obviously will be very low. I guess maybe 30 to 40%. Yeah, the training set accuracy is low 21%, and validation set accuracy is 37% because we train the model for only one epoch. And then we compute the accuracy for the test epoch or the test set, and it is, I guess, 37%. Then we examine this model and we get the different predictions. For example, we see the predictions or incorrect predictions using the PCA and Disney plot, and here we get the images, get predictions. For each prediction, we get the predicted class. Now we plot the confusion matrix, and here we plot this confusion matrix. We can then find which prediction were correct and then sort the incorrect predictions in descending order. We sort out the incorrect predictions in descending order, plot the most incorrect predictions. Interestingly, the most incorrect prediction in most incorrect was an example that is incorrectly labeled in the dataset. So, for example, truck and automobiles, they are very confused, but even to humans, they are very confusing. So, for example, true label was aeroplane, but it was detected as a ship, and true label was automobile, but it was truck. But car or truck is also automobile. So here is the case. So next we will get output and intermediate representation. Now we are going to get the intermediate representation. For this intermediate representation, we are going to perform the PCA plot, and we plot the representation. Like the previous notebooks, the class seemed more separated in the output representations than in the intermediate representation. Output representation, the classes are more separated, but in the intermediate representation, they are less separated. So intermediate PCA data, get PCA intermediates. So we can do the same with the t-SNE. Again, we only use a subset of data because t-SNE takes a lot of time to compute. So get intermediate representation, and we plot only two components. We take only 5,000 images, and we are going to plot the t-SNE for intermediate representations. So here it is the t-SNE representation, and it is the intermediate representation of t-SNE. So it is the intermediate representation. We can also imagine an image belonging to a specified class. Okay, so you can go through this defining image. So we get an image that our model is 100% confident is a frog, but just look like say random noise. So we print the best image probability. In this case is 14% because we trained the model for a very low time, and then the best image to normalize. So it looks like this. Next, we plot some images after they have been convolved with first convolutional layer. So we take some images and we convolve it with the first convolutional layers, and we see that how they looks like. So we see different types of edges and blurring that the filters have learned that they are apparently decent features extracted model. So number of take 5 images and we take 7 filters in the first convolutional layer. So take 5 images and we take the 7 filters. So the first filter it find some edges, vertical edges. These are some shapes. So these are the different features of this image. So these are the different filters. They correspond to different shapes, different features of this image. So it works like this way. Finally, we can plot the actual filter our model has learned. Now we are going to plot the different filters that the same that we did in the last time. And again, nothing really interpretable here. So these are the different filters that have been applied in our images, because this time the images are color images, so filters are also three-dimensional color filters, but there is no clear interpretation what these filters means, but they work really very nice. So we can now learn interesting. We can we ever learn interesting looking into filters, our or we doomed to just look at colorful blocks forever. So there is a debate for that. What does these filters mean? So you can read it more about it. So here it is the AlexNet model, and we print out this model that what these convolutional layers, max pooling, convolutional layer, LU, and max pooling like this. So we can get that the learned values of these filters the same way we did for the version of the AlexNet. Then we plot them. So we plot these filters. The filter size is larger 5 by 5, and then so again these are also the it is difficult to answer these questions as modern computer vision architecture now seems to be favor smaller filter size with their largest filters being 5 by 5. So maybe larger filters are not that good after all. So this is all about using the AlexNet for C for 10 dataset image classification. In this notebook, we have loaded the torch vision dataset, loaded transform, defining CNN, AlexNet, customizing the initialization, how to use the learning rate finder. We trained the model to achieve good accuracy, viewing our model mistakes, visualizing our data in low dimensional, generating fake images, viewing the learned weights, and loading the pre-trained model. So this was all about CNN. So maybe next notebook we will talk about the VGG. Thank you so much.